Greetings from Goblin Valley, Nissedal, Norway. I'm here so you don't have to be. I'm not showing myself today because I have forgot to braid my beard, and only my girlfriend, the dragon, can see me like this. It's a promise. And for now, please just ignore the background. It's just something while I'm adjusting some airflow stuff while we talk a bit. This video is about the most typical single coil designs that are out there, and that is the symmetrical dual airflow kind, with airflow from the sides and the coil placed in the center of the RDA. I have had a lot of requests for doing an experiment like that, and mainly because when I did the Entheon RDA Revisited, I told everybody you could solve this by mathematics alone. And some people didn't believe it, and others cried out for talking about different results, and so on and so forth. So if nothing else than to calm myself, I actually built a new experiment. Proper to size with the typical RDA like the Entheon, and setting all that up took a lot of time. Well, it doesn't take much time to actually watching stuff like this happening if you have a cool assistant that can produce vapor or run a smoke machine for you. But the trick is to set the lights and actually photograph this stuff so other people can see it for themselves. And making all of those things come together is highly problematic. Now let's talk about the setup while we have it in front of us. Look at the enormous tubes coming in from the left and the right. They are so big because of a phenomenon called vorticity, and that is in a tube where there is flow, you get transversal flows, two of them, clockwise and counterclockwise, and that's the reason it's harder to blow through a long straw than a short straw, because there are forces in, well, not forces, effects in long tubes that counteracts the flow. So it took a long while to make the proper tubes and have a continuous flow through the center of it. The openings here are 2 by 5 centimeters on each side, always vapor coming in from the left side and clean air from the right side. And there will be some leakage somewhere, somehow, because this is highly complicated to set up, at least to my standards and my tools. But now let's watch a proper placed coil with the proper airspeed. Yeah, here we are. Now this looks better. The coil is dead center between the two air holes, and air will come in from the left. And before all of you naysayers jump up and down and tell me, you've been wrong again, the air is moving upwards. Well, just hold your horses and I'll explain to you what is going on. What you see in this picture is a clear flow of air from 9 o'clock to 12 o'clock. And you also see a somewhat clear stream of air from 9 o'clock down to almost 6 o'clock. The reason you might think, oh, the air is going up towards the suction, that is actually not due to the suction, but due to the predictions I made regarding this scenario. Because air coming in from left and right, those air flows are split in two. That means half of the air is going down below the coil. This creates a two-chamber situation. That is, there is high pressure below the coil. This pressure seeks to escape to the lower pressure above the coil. And you see the vortex down to the left. That flow of air is pushing the main flow some degrees upwards. And the reason it might appear that the air above the coil is sucked up is an optical phenomenon, because that air is more concentrated and shows up in the lights much more clearly than the air being pushed down that goes turbulent immediately because it encounters the flow of air, clear air from the other side. But the high pressure below the coil is actually pushing the center flow a bit upwards. Now I have moved the coil a bit up, so it's tangential with the bottom of the bottom of the air holes. So now even more air is pushed down below the coil. Now, if you're going to talk millimeters, the coil is now, it's 4 centimeters, but it's okay, 4 millimeters. It's 3 millimeters above the floor. And the vacuum is going 8 millimeters then above the coil. And now most of the air is pushed under the coil, so there is a lot more pressure under the coil than above it. So the airflow from the holes is now being pushed further up than before. And the result of this is actually less effective cooling flow over your coil. Because a greater part of the coil below 9 o'clock is now experiencing much more turbulence than concentrated airflow. It's a directional turbulence. And the same is happening above the coil, because the turbulence flowing up on either side of the coil is disturbing the airflow, not gently pushing it, but creating more turbulence. And you can see by the fluffiness of the cloud at 10 o'clock that this is actually happening. This effect that I predicted and had some help to predict is clearly a reality. And for some of you this can be used. We will get back to that in a short while towards the end of this experiment. Because I'm experimenting with smaller coils, the 4 millimeter equivalent, to a 5 or 5-ish millimeter equivalent coil. But first we will push this coil even further up. Now all air is coming in, colliding under the coil, building up pressure in what I call now the first chamber, the space below the coil, which is now huge. And as you can see by the fluffiness of the clouds, all air hitting your coil is now turbulent or directional turbulence. You have no longer the fine lines and the nice patterns we started out with. Because, as we all know, and you will see by watching all my other videos, air flows in a straight line, giving pressure difference. But now we have a head-on collision, and it ruins everything. At least for us who uses flat wire coils, or round coils, or an ordinary parallel coils, or the very, very fine wrapped Clapton coils. This is not the situation we want. This is not for us. This situation is for bigger coils with a bigger outer diameter, and coils that are unable to create an aerodynamical flow around itself. So I'm gonna have a little vape here while you just look at the footage, and then we'll go on to a bigger coil in 20 seconds. Yeah, give it a couple of seconds more. This is the coolest stuff ever. Yeah. So let's head on to the big bastard. Now, please watch the space below the coil. And this is the reason, and now you can see it visually, why you have trouble using big coils in these single coil RDAs. Look how dense the vapor is below the coil, and look at the clear space above it. And also, when the amount of vapor dies down, watch how the space below the coil at 6 o'clock now clears last of all the vapor in the chamber. That is the 0 point and the stalemate that I predicted when I did the Entheon RDA Revisited video. And I never get tired of watching this, because when you have a hypothesis and you can by some experiments predict the result, and then you get the result like this, it very, very much strengthens the whole hypothesis. So by using 3 simple math calculations, this could be predicted once I knew how the air would behave. And you know, it's so cool. And if you watch at 10 o'clock, you can also see that the very, very high pressure below the coil creates an enormous amount of turbulence from 9 o'clock and upwards. All the fine lines we had to begin with has now gone because of this pressure differentiation within the main chamber itself, because the chamber has been split in actually 2 different chambers. So let's move the coil up, and this looks much better. Now you have an active vortex to the left, bottom left of your coil again. And being more active, it of course pushes the mainstream upwards. But it also clears the area under the coil much, much faster. And you can see the right half under the coil is almost clear all the time. So the same thing is happening with the clear air coming in from the right. This is promising if you use bigger coils or Clapton coils. Because look at the narrow spaces on each side of the coil. It's equivalent to 1 millimeter. So the turbulence streaming up here, taking the main flow with it, is actually very active and cooling for the coil. So in this scenario, if you use a Clapton, you now have quite active cooling from 6 o'clock in the bottom and up to 10 o'clock, where it clearly is very disruptive and very fluffy. Yeah, let's have a little vape again. You see, I need to think sometimes when I'm talking and watching this stuff, because even after watching this for hours, I still spot new stuff that is very interesting. Oh yes, one thing that strengthened, because of my theory on airflow, watch to the left, above the left wooden block, you see turbulence coming down. And that means that the air that you initially, at first when we started this video, oh, the air is sucked up, it's sucked up, you're wrong. No, it comes back down when you first start to have this kind of turbulence. So everything we have seen up until now just proves all my hypotheses in this stuff. And yeah, let's ramp it up and give it some more vapor in the chamber there. But it's cool to see the clear points at the 12 o'clock and 6 o'clock, because the airflow is, after all, symmetrical. But to do yeah, okay, let's go. This is the situation you want if you use a Clapton coil in a single symmetrical RDA. You have, it is not a direct clear flow to the bottom of the coil. That flow is disrupted because of turbulence, but it is highly active. So here you finally get cooling directly to the bottom of the coil, and watch the jets shooting up diagonally to both sides of the coil and spreads out in a fan formation. I think that is pretty awesome. So in this scenario with a Clapton coil or a big coil, you get very highly active cooling to the bottom up to respectively 3 o'clock and 6 o'clock. But this spins and spins up almost to 12 o'clock. So let's say you get a pretty active cooling of your coil up to maybe as much as 60 to 70% of your coil. So you can run it hotter and ramp up more and get denser flavor and all that stuff. But the effect of a high pressure dual chamber configuration like we have now is really pretty awesome. So yeah, you can see that you have a direct flow to both sides shooting up, and at times there are equal amount of vapor flowing up to the right and the left side, because you have a total mixture below the coil just shooting up to the sides. So this is a solution for you Clapton crazy fellow vapors of mine, or who insists building big. Now let's watch the first video one more time. Now watch these 3 puffs of vapor one more time. Look at how concentrated the flow really is alongside the coil. And look how you have clear shooting of jets down from 6 o'clock and 12 o'clock. And notice the vortex in the lower left corner. This is the active flow you get when you go use flat wire, round wire, parallel regular wire coils, and uses a diameter smaller than 4 millimeters. And also notice that the central airflow is somewhat pushed up, not a lot. We're talking about 5 to 10 degrees maybe. And the disruption is not so crazy big that it ruins everything, and you don't have the Quanta effect up until 12 o'clock. So this is probably the last air chamber experiment I'm going to show you for a while, and up until now I've just shown you the effects, because building actual specs like this is really hard work, and I have collected the data I need. And I hope some developers watch this and fix this, because the way you can fix the situation in single coil RDAs are so simple that you would bite your finger off if you knew it. Yeah, bye for now.